So let's go ahead and finish this up real quick. So I think the last thing that we talked about here was we answered part A, the rate law for the reaction. And what we figured out here is the rate law for this reaction is going to be rate is equal to K times, I believe it was A squared. Because what we decided was when the concentration of A doubles, the rate quadruples. And when the concentration of B doubles and nothing else changes, then the rate doesn't change at all. Okay, so B is not, it's a zero order reaction with respect to B. And anything to the 0 power is just 1, so it doesn't need to be written in the rate law. Okay, B, the magnitude of the rate constant. Okay, now that we have our rate law, we can just pick one of these experiments here to find our rate constant K, right, which is this right here. So let's do B right here. I don't have a lot of room on this page. So our rate, let's just pick experiment 1. It doesn't really matter. You can pick any of the experiments and it should give you the right answer. Our rate is 4.0 times 10 to the negative 5th, and that is equal to K times A squared, which is 0.100 squared. Nah, okay, I'm not being careful here. I need to be careful with my units. Sorry. I'm punching on a cough drop. This is molar per second. That's equal to K times 0.100 molar squared. Okay, so when we solve for that, we're going to divide both sides by, it's going to end up being 0.0100 molar squared once we multiply that times itself. 0.100. Now this is an example of the kind of thing that they could actually ask you on the multiple choice section, because it's the math works out so easily. So then you divide that by 0.01, and you should end up with 4.0 times 10 to the negative 3rd, I believe. Let me make sure. Double check my math here. Yeah, 4 times 10 to the negative 3rd. So 4.0 times 10 to the negative 3rd is our K, and we have to be careful with our units here. Okay, we divided molarity by molarity squared, so one of those gets canceled out and we end up with molarity on the bottom and seconds on the bottom. So this is molar -1 seconds -1, which is a typical rate constant for our K when we have a second order reaction like this. Okay, and then C here, the rate of the reaction when the concentration is 0.05 and B is 0.1. Okay, now that we know the K, we just solved for K, now we can solve for the rate when we are given this set of concentrations. So rate equals 4.0 times 10 to the negative 3rd, molar to the -1 seconds to the -1. Multiply that by our concentrations here. Now, the nice thing is, in our rate law, the only concentration that matters is A. B doesn't matter at all. So 0.050, and we square that. Okay, and when you multiply those two things together, that should give you the rate. And it should be 1. Is that right? Yeah, that's right. 1.0 times 10 to the negative 5th. And again, the units here should be, because molarity squared is going to cancel one of these, and then we're going to have molarity left, so it's going to be molarity per second. That's our rate. Okay, next. Just a couple other types of questions here. Based on the table below, which shows the results of a rate study with the reaction A plus B yielding C if the reaction is second order with respect to A and first order with respect to B. Um, wait a second. Oh, I'm sorry. Based on the table below, which shows the results of a rate study with the reaction A plus B yields C. If the reaction is second order with respect to A and first order with respect to B, the initial rate of formation of C in the second experiment would be what? It's kind of a horrible run-on sentence. Okay, so it's second order with respect to A and first order with respect to B. The initial rate of formation of C in the second experiment would be what? Okay, so what we need to do here is probably write a rate law to start with, okay? So the rate here is going to equal K times, if it's second order with respect to A, then the concentration of A gets squared. First order with respect to B, concentration of B to the first power, which you don't have to write the 1 necessarily, okay? The initial rate of the formation of C in the second experiment would be 1. Okay, so now we have to look at what's actually happening here, okay? And so actually we can kind of figure out what would happen with A and B and find out what X is, and then we should be able to tell how the second one relates to that, okay? And so our rate here should be equal to, if A is a concentration of 1, 1 squared is just 1, multiply that by B, which is 2 to the first power, so that's going to equal 2, okay? So, I guess 2K. So if X is equal to 2K in this first one, then when we change the concentrations here, in the second experiment, our rate is equal to K times 0.50 squared times 4 to the first power. That's going to give us, I think, 1K. Alright? So if X equals 2K, then this one down here is going to be half of that, or 1/2 X. Okay? So that's what they're asking you for, is how does that relate to the one above it? That's kind of a weird question. But hopefully that makes sense. We can talk about that in class if it doesn't. Okay, and that's it for change of concentration. And we're going to talk about how that relates to time next time. Again, sorry for the length of the video. Hopefully that all makes sense. We'll do a lot of practice on it in class.